Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. The key to using torus symmetry is the representation theory of tori. And in this video here, I wanted to tell you about the main theorem which classifies all finite dimensional representations of the torus. And it's a beautiful theory which generalizes diagonalisation theory that you find in linear algebra. Okay, so let's go to the setup that we want to use, at least for today's video. So the setup here, T will be an n-dimensional algebraic torus. So that means that we're going to have an algebraically closed field K, and then we're going to look at the multiplicative group of K, so K cross the non-zero elements, and we'll look at n copies of that. That's the n-dimensional algebraic torus. We'll look at finite dimensional vector space V. So T will act on this V, which means that we have a representation of T on V. So more precisely what this is, so we have a group homomorphism T to GLV. So this is the set of linear isomorphisms from V to V. Okay, so this is a group, and in fact it's an algebraic group. So you want this to be a morphism of algebraic groups. So not only is it a group homomorphism, but it should be also a morphism of group varieties. Okay, so that means that in particular we can think of this V as a T module. Okay, so T acts on this V. How does it act on V? So if you have an element of the torus little t, it acts on a vector little v inside big V by, well, you look at rho of t, which will be some linear endomorphism, automorphism in fact of V, rho of t, and you let that automorphism act on this V to give you a new element of V. So that's how T acts on V. So remember, it's an action. In what sense? So one of the things that you have is you have the usual associativity law. Okay, if you let a product of two torus elements S and T act on this V, that's the same as if you let T act on V to get a new vector, and then S act on that new vector to get another vector. Okay, so you have this associativity law, and that's in what sense that T acts on this V. Okay, so what's the main theorem? So what we're going to do is we're going to classify all such representations of this n-dimensional torus. And the way we'll do it is using the following theorem, okay? So the following theorem tells you that you have a simultaneous eigenspace decomposition. This V equals the direct sum of these V chi's, so these are going to be subspaces, and I'll explain a bit more what that means. So one way to think about this is that firstly, you have not just one linear endomorphism of V, you have lots of them. One for each element of the torus. You can look at all these rho of t, so you have lots and lots of them. So what we're going to do is we're going to look at something which is an eigenvector for all of these rho of t's. Okay, and that notion gives you the notion of a simultaneous eigenspace. Okay, so this is what I mean by a simultaneous eigenspace. So more precisely, what's that mean? So firstly, this chi, also the index for this direct sum is going to be by what's called the characters of this T. So they're the algebraic group homomorphisms from T to K cross, and that's often denoted by T check, the characters of T. And so what does it mean that this V chi is a simultaneous eigenspace? So that means that for any vector inside here, if you let any element of the torus act on this V chi, it's going to just multiply that V chi by this chi of t. So chi of t, remember this chi is a function from t to k cross. So for each t, you get some scalar. Okay. So in other words, this V chi is either 0 or it's going to be an eigenvector for this action of t. So an eigenvector of rho of t with eigenvalue chi of t. And this happens for every vector inside this V chi. And you can find enough of these simultaneous eigenspaces that V is the direct sum of these simultaneous eigenspaces. Now often these chi's are also called weights, and so this is also called the weight space decomposition. Okay, so this is very nice. If you remember, if you have a diagonalizable matrix, you get a similar direct sum decomposition into eigenspaces, and they're eigenspaces for that single endomorphism. Now we have this direct sum decomposition where all of these row of t's act by scalars on each of these eigenspaces. Okay, so I'm going to give you a full proof of this theorem. It's a wonderful theorem, and it really underpins the representation theory, or is the finite dimensional representation theory of tori. Okay, it's a complete answer to that question. Okay, and the lemma that we need here, hopefully you already know this from linear algebra, but it's such a wonderful lemma. I like to always repeat it whenever I have the opportunity. So suppose now you have two linear endomorphisms of V, so phi, psi, linear maps from V to V, and suppose they commute. Then what happens is that if we let V lambda be the lambda eigenspace of this phi, then in fact psi will preserve this V lambda. Psi of V lambda is contained inside V lambda. So this is one of the key points. Okay, if you have two commuting endomorphisms, okay, then each, by the way, it's symmetric in phi and psi, so you can also swap the roles of phi and psi. So basically, each will preserve the eigenspaces of the other one. Okay. So let's see why this is true, and this is easy enough. And you just have to check that every element in here is in here. So we're going to pick some element inside here, so inside V lambda first. So a lambda eigenvector or 0, V, little v. And we're going to apply psi to it, psi of V lambda. And to check that it's inside big V lambda, we have to check that it's a lambda eigenvector or 0. Okay, so it when you apply phi to it, scales by lambda. So let's apply phi to it. So what's phi of psi of V lambda? Well, this is where we need to use the fact that phi and psi commute. So this is psi of phi of V lambda. Now V lambda is in big V lambda, so the action of phi is by scaling by lambda, so this is just lambda V lambda. And psi is a linear map, so you can pull out this lambda, so that's lambda of psi of V lambda. So the action of phi on psi of V lambda is just to scale that psi of V lambda by lambda. So it is indeed either 0 or a lambda eigenvector. Okay, so that tells you that this inclusion does indeed hold. Okay. So the proof of this theorem is essentially lifting the usual eigenspace theory that you know from linear algebra to this more complicated context where you have lots and lots of linear endomorphisms. Okay, so let's use it for one particular endomorphism, one particular row T. So let's get back to the proof of the main theorem. So suppose you pick an element of the torus and we pick one that is M torsion. Okay, so what's M torsion? And M here will have to be something which the characteristic of K doesn't divide. So that means that some power of it is equal to 1. Okay, so for example, if the torus is just one dimensional, okay, M torsion just means it's an mth root of unity. Okay, and note that this M can be any integer that, as long as the characteristic doesn't divide it. Okay, so we're going to use linear algebra in this context, and so one of the things that you should realize is that if you have an arbitrary linear endomorphism, it's not necessarily going to have an eigenspace decomposition. Okay, it has a generalized eigenspace decomposition, but not necessarily an eigenspace decomposition. So what's special in this case here is that if you look at this t to the m equals 1, okay, then the minimal polynomial has to divide basically 2 to the m minus 1, which has distinct roots. And since it has distinct roots, you know that it does actually have an eigenspace decomposition. So rho of t here, rho is a group homomorphism, so rho of t to the power of m is also equal to the identity. And so it has an eigenspace decomposition, v equals the direct sum of these eigenspaces v lambda. Okay, so that's the first thing. If we pick any m torsion element in this torus and you apply linear algebra to that, then you get at least an eigenspace decomposition for that. Okay, so what's the next thing that we're going to do? Well, suppose now you have any t prime, which is a torus element. What does the lemma say? So this, remember this, t is an abelian group. So if you apply rho to those elements will still commute. So this rho of t and this rho of t prime for any t prime in the torus will still commute. And so if we apply the lemma to those two endomorphisms, rho of t and rho of t prime, then we'll find that rho of t prime preserves this v lambda. So in other words, every element of the torus will map v lambda back to itself. So you can think of now T acting on this V lambda as well. It's a T submodule. Okay, V lambda is also a T module, a T submodule, in fact. Okay, so each of these eigenspaces is actually a T module. Okay, so that's good. So why is that? Because one way we can prove this, okay, is by induction on the dimension. We're going to use induction on the dimension of V. Okay. Now, if this is a non-trivial eigenspace decomposition in the sense that there's more than two eigenspaces, then for each of those eigenspaces, we know we can write it, we can give a simultaneous eigenspace decomposition like this one, okay? And maybe we have to put some things together, but essentially we'll have, we can work on each of them, and that will give you what you want, okay? So we can assume that in every single case, for all of these M torsion elements inside the torus, you just have a single eigenspace. Okay, so that's what we're going to assume, okay? So for every T, which is M torsion, for any M satisfying this thing, so, okay, so T tor is the torsion subgroup of T, okay? So they're all the ones which are M torsion for some M satisfying this, okay? We can assume that this V is a single eigenspace, okay? And let's suppose that corresponding eigenvalue is chi of T, okay? So in other words, T dot V equals chi of T V for all V inside this big V and all T which is torsion, okay? Now this is the type of equation that you want, okay? So this is the equation that we have here. This is basically the simultaneous eigenspace condition, okay? So this is the type of condition that you want, but you kind of want it for all T, and now we've just got it for all T which is torsion. And we want to kind of lift that up to the whole of the torus. So there's a trick now to lift that up to the whole of the torus. Okay, so we've got this at V, and it satisfies this condition here. So what are we going to do now? So the first thing we're going to do is I want to find some eigenvector, simultaneous eigenvector for all elements of the torus. Okay, so that's the trick that we're going to do. So the way I'll do that is if it's a simultaneous eigenvector, that means the span is going to be a one-dimensional T submodule. And I claim that you can find a one-dimensional T submodule of this V. Okay, so why is that true? Okay, so firstly, if it's already true that actually the whole of this torus acts by, each element of the torus acts by a scalar, right? Then it's easy to do this. And in fact, we're done. Okay, we can skip to the last part. Okay, but if that's not the case, okay, suppose you can find an element of the torus such that it's not a single eigenspace, then you can find some proper eigenspace. And that proper eigenspace will also be a T module, T submodule by the lemma. Okay, and it's going to be smaller, non-zero subspace. Okay, and then you can apply induction, and you can get smaller and smaller until you find a one-dimensional T submodule. And that one-dimensional T submodule, let's suppose it's spanned by, say, V bar, okay? Since a one-dimensional T submodule, okay, the only thing that elements of T can do is scale this vector. And suppose it scales it by the eigenvalue chi of T. So we know what the eigenvalue has to be if T is T torsion, okay, so it has to be this chi of T here, because that's what it does to every vector. But for this particular one, V bar inside V, okay, we also have some sort of eigenvalue. So now we know that T, if you act on this V bar, this single element inside V, it just scales it to chi of T times V bar. And this holds now for all T inside this torus, okay? So we have this equation, which is good, but it's only for all T, which is torsion. And we have this equation, which is good, okay, which holds for all elements of the torus, but only for this single non-zero vector V bar inside V, okay? And we want to try to broaden it so that actually you have this hold for all elements of the torus and all vectors V, okay? So the other thing is this function chi. We haven't said too much about it, but remember, what we want is that these eigenvalues are essentially given by some character of this T, okay, some algebraic group homomorphism from T to K cross. Okay, and how does that work? So let's check that chi is indeed an element of T check. And that just means that it's a group homomorphism. Okay, once we can show it's a group homomorphism, it will be an algebraic group homomorphism because it's going to come from the representation theory. Okay, so this is a morphism of algebraic varieties, and so this chi has to come from that. So it will also be a morphism of algebraic varieties. And the key point is that this is essentially just a consequence of the fact that this action is associative. So if you let the product T1, T2 act on this V bar, that's the same as if you let T2 act on V bar first and then T1 act on it. Okay, so let's see why that's the case. So I've written out the computation here. So if you let T1, T2 act on V bar, okay, so remember this is a simultaneous eigenvector, and the eigenvalue for T1, T2 is chi of T1, T2. So this is chi of T1, T2 times V bar. And what about on the right-hand side? Well, this is an eigenvector for T2 with eigenvalue chi of T2. So this is chi of T2 V bar. You can pull out the chi of T2, and then T1 acting on V bar is chi of T1 times V bar. So since V bar is non-zero, okay, so the scalars out the front have to be the same. Remember, these are also scalars inside K cross is commutative, so chi of T1 times chi of T2 is chi of the product T1, T2. And that tells you that chi is multiplicative, so it's actually going to be a character. Okay, so that's part of this, of what goes on here. You want this equation to hold where this simultaneous eigenvalue, the eigenvalue for this simultaneous eigenvector is going to be a character. Okay. So let's restate what's going on here. Okay, so remember, we're saying this V is going to be a single eigenspace for every torsion element, and that eigenspace corresponds to eigenvalue chi of t. So if you look at this equation, what does it mean? Is that if you let t be in this torsion subgroup of this big T, which I note, by the way, is dense, actually, okay, then what does rho of t do? What does the action of t do? It's just the identity times chi of t. So it's chi of t times the identity. Okay, so this is an equation that you have. Okay, it's an equation essentially on this algebraic variety. Okay, and you know that it holds on a Zariski dense set. Note that this has to be Zariski dense. Okay, so if you look at, for example, k equals c cross. In that case there, k equals c cross, the torsion subgroup will just be all the roots of unity. Okay, so all the union of all the mth roots of unity as m gets arbitrarily large. Okay, and that's not dense in the Euclidean topology, but it is dense in the Zariski topology. But here you're playing around in the algebraic setting, so this is defined by polynomial equations, so you know that actually this has to hold all the time. So this is how we lift to the whole torus, by using density. Okay, and so in fact this statement holds for all t, and that's precisely what you want. So that means that this equation holds not just for t inside the torsion subgroup, but for all torus elements. Okay, and so that will give you this statement here. In fact, we did induction, so we've reduced the case we have just a single eigenspace. Okay, because we've reduced to that case, and that proves the theorem. Okay, so it's a lovely proof which kind of basically bootstraps a lot of the linear algebra that you see, okay, to the setting of lots and lots of commuting endomorphisms, and that's how you get your answer. And you use a little bit of algebraic geometry at the end, the Zariski topology, to finish off the proof. Okay, so just some final remarks. So firstly, what is this T-check? So this is why it's very important to know the character group. So this is actually a group. And in fact, this group is z to the n, which is discrete. So one of the key things about torus symmetry, which is really nice, is that if you're in a situation where you have a lot of torus symmetry, then often you can reduce the problem that you're looking at to something which is combinatorial. And this kind of is a key reason why this is true, okay? This character group is actually something which is discrete. The other thing is that here I'm looking in the case of algebraic groups, but one thing to note is that this representation theory, you can work in various versions depending on the geometry. Okay, so it's a bit like different operating systems, okay, that you have in your computer software. There are various versions. They have similarities, but they also have some differences as well. Okay, so but in this case, there's a certain similarity. If you look at complex representations of the n-dimensional real algebraic torus, you'll get a very, very similar theorem. Okay, so this gives you the wonderful theorem here that if you want to look at the finite dimensional representations of a torus, okay, V. It's in fact the direct sum of simultaneous eigenspaces, and this beautifully generalizes linear algebra as you see it in your standard linear algebra course. I hope you enjoyed this adventure in pure mathematics.